Okay, so now we discuss the Euler's axioms, and the first thing which we do is to define the momentum and the moment of momentum. So let's see how we can do that. So the momentum P in the F frame and the moment of momentum H A by F of a body B, which is your system. Okay, so you know that everything which you consider is a system and anything outside is called a surrounding. So body B is your system about a point, and what are these points? These point A can be a material point, of the body. It can be a fixed location, of frame F, or a point of another body in motion with respect to F. So we are somewhat liberal about what this point A can be, for which the moment of momentum HAF is defined. With respect to frame F. So with respect to frame F is there in both momentum and moment of momentum are defined. Okay, so it's a defined entity. So P F frame is equal to M VP by F dm, and then HA by F is equal to M R PA cross V PA by F dm. Okay, so the momentum and the moment of the body is defined like this. Obviously this is with respect to a frame F, that's why you have a subscript of F in both of these definitions. Okay, so one can also write the momentum as this integral R P dm over time in the F frame. Okay, so this time derivative is in the F frame. This also becomes M RC based on the definition we have just learned before. Okay, in the F frame we have learned about what integral of RPDM is. Okay, so it can be written as MRC. So the center of mass is already written as RC. Position of center of mass is RC. Now this implies that the momentum with respect to F frame is mv of c with respect to F. Now the reason we can do it, if you take a time derivative of this term, you will get a m dot and then rc plus rc dot m, but m dot has to be 0 because we had defined the mass such that it is independent, okay, of the frame, so it's constant. So m dot is constant, that's why this chain rule of differentiation gives us this particular answer. Now this is equal to the mi vci of f based on the discrete parts i's. Okay, so if there is a part 1, 2, 3, 4, they can all be written like this. So this is 2.9. Let's see how we can visualize all this. So if you have, for example, a frame f point O and this is the body. Okay, now this is a small part of it which is dm, and you have rp c. Okay, now the velocity of this center of mass is vc with respect to f. This is called rc. Okay, and this is rp. Now if you have the velocity of this particular point, which is p over here, sorry, velocity of this point, which is p, velocity of this point is actually equal to vp with respect to f. Okay, so you will be writing the momentum using this. Write the velocity of p and multiply by the small mass which is there. So this small mass contains this point p. Now integrate it over the whole mass. That's where you get the momentum. And then you want to write it in this form. You have to write the position vector of p, which is rp, multiplied by the small mass dm, integrated, and then take an overall time derivative. Okay. That time derivative which you take will come out to be as equal to this value based on your previous equation of the center of mass. Okay, so that is something which you can do, and thereafter, so this, I mean, you can do it by equation 2.4. So you should please go back and check how this equation 2.4 is written. Okay, and after this you can take this time derivative, apply the chain rule, and m dot must be equal to 0 because the total mass of b is constant with time, and that's how you get mvc by f. And this particular thing mvc by f can be written is equal to the summation of the small individual parts, each having a center of mass at rci, or the velocity ci. So this is by 2.6. okay, equation 2.6. so please go back and check 2.6 and see whether this makes sense. Okay, if not exactly 2.6, but it is a derivative of 2.6, so you should be able to write this. Okay, now this is the first diagram which you have, and that shows basically this particular part. Then you can have the velocity of center of mass over here, that can be visualized like this. So the center of mass is moving with a velocity vc with respect to the f frame, and the total mass is m. Now if there are individual parts like this is m1, okay, this is m2, this is mi, so this is c2, this would be velocity of c2. Okay, so all these velocities are in the f frame, I am not writing them separately. Okay, so that is where this can be written. So if the total mass of the system is like this, then you can break them down into individual parts, each having its center of mass at C1, C2 or Ci in general with velocity Vci, and that summation can be written. Okay, so this is how one can do the visualization part of it. Let me separately also define the moment of momentum. Okay, since the diagram is already there, why to? So if you have any point A, okay, we have seen that A can be a point on the body, it can be a point on the frame F, or it can be point on another body which is in motion with respect to F. So it can practically be just about anything. Okay, point A can be anything. So this has a velocity of A, and this particular vector will be RPA. Okay, so that's how the moment of momentum about A for this body, this is the body B, can be found out. So RPA cross VPA, and so you have already VA and you have VP, so VPA will be VP minus VA, both in the F frame. Okay, so you have VP and VA, so you should be able to find VPA. Okay, so you have a means to solve this yourself. Okay, now we want to also write this definition, the equation 2.9 in words. So the momentum of a body equals the momentum evaluated as if the total mass m of the body were concentrated at C and moving at its velocity Vc in respect to the frame F. Okay, so that's the meaning of this particular equation. The total momentum of a body equals the momentum velocity as if the total mass m of the body were concentrated at C moving at its velocity. So that's the meaning of this particular statement. Okay, so we will now be, before we define now the Euler's axiom, we have already done the part of defining the moment and the moment of momentum of a body about a given point. So what do these Euler's axioms do? They relate the time derivative of momentum and the moment of momentum with external forces and moments. So I'll write this in some other color so that we know what do they do overall. The Euler's axioms relate P dot and HO dot with the external forces and moments. Okay, so let's see, let's just mention those two axioms here itself. Axioms, there exists a frame I such that for any system P dot I is equal to F, this is equation 210, and H dot O in I frame is M naught, this is 211, okay, where O is a point fixed in I frame. F is the sum of all the external forces from the surroundings on the system. And MO is the sum of the moments about O of all external loads. So the loads can be either forces or moments from surroundings of the system. So this word sum of all the external forces from the surroundings on the system, and MO is the sum of the moments about O of all external loads. So it can be either a direct moment or it can be the moment due to a force which is external to the system. Okay, so this external word is very important, and that's the overall idea. So you may have learnt or known this in some other form, and but this is just another way to see it, and that's approach which we are following in this course, from primitives to defined entities to axioms, and then eventually theorems. Okay, so this is the Euler's axiom, that there exists a frame I such that for any system, okay, this any is important. So the change in momentum in the I frame is equal to the sum of all the external forces on this system, and the change in moment of momentum of the system about a point O in this frame is equal to the sum of all the external moments, which can be either direct moments or the moments due to forces. Okay, now this is the first time we are doing it in this course. The frame I, the frame in which the Euler's, the frame I in which the Euler's axioms are valid is called an inertial frame. Okay, so this is the first time this word has come up in our discussions. What is an inertial frame? An inertial frame is the frame in which the Euler's axioms 2.10 and 2.11 are valid. Okay, that's the short answer. So the two laws which we have, I mean the two axioms which we have mentioned are actually independent of the origin. Okay, we never mentioned about the origin, nor did we mention about the orientation of the coordinate axis in the I-frame. So whatever be the, wherever be the origin, wherever be the, whatever be the orientation of the coordinate axis, these should be valid, and if they are valid, then that is the inertial frame. Okay, so the experiments on which these axioms are based remain valid when we shift and rotate the coordinate system attached to I. Okay, so any experiment which was done to measure the rate of change of momentum and that was found to be equal to the sum of external forces, those were valid even when you were shifting the origin or were reorienting the coordinate axis attached to this I frame. So that is why we claim that this is independent of the position of the origin or the orientation of the coordinate systems. Now there are some comments about the inertial frame which you may already be knowing, but I think it's worth discussing over here again. It is impossible to find an exactly, or let me emphasize on that word, to find an exactly inertial physical frame. So you cannot have an exactly inertial physical frame, meaning you will not have a frame in which these Euler's axioms are exactly valid, but there are approximations in which these axioms are valid. So let's take the closest approximation, and there are some examples. Okay, so the closest approximation so the frame attached to the center of mass of the solar system with its orientation, okay, orientation meaning the orientation of the triad, okay, the coordinate system fixed relative to specific distant stars. Let me put emphasize on distance just to tell you that they are too far. Okay, and what is the idea of these distant stars? That they are fixed. in some of the English literature. I think I remember one of Shakespeare's plays where they refer to the northern star as something which was fixed. Okay, so nothing is fixed in reality, but the idea of distant stars is that they are fixed stars since they are so far that no change has been observed in their angular separation. So since they are so far that no change has been observed in their orientation. Okay, so these are some sort of markers or bios in a sea, okay, which are so far that we assume that they are actually fixed, and with respect to that we attach the frame which is to the center of mass of the solar system. Well, you can also say it's the center of mass of a whole galaxy which has lots of solar systems. So whichever way you would want to define this, okay, since it's not exactly there, we are trying to define it in approximation. So that's the closest approximation which you can think of. Okay, then you can have, say, the second closest. Now these are not the only examples, but you can see why this is the closest approximation and why the next is the second closest approximation. Okay, so this is a frame attached to the sun's center with orientation fixed. Relative to distant stars. Okay, then we can write the third closest approximation, and as you can see, we will move from the center of mass of the solar system to the center of mass of the sun, the center of the sun, and then to the center of the earth, and so on. And you will see why it is why we are getting further away from this, because we are definitely moving towards frames which are accelerating in themselves. Okay, so the center of mass of the solar system perhaps was less accelerating, and the center of mass of the sun is slightly more. It is known, we just know it to be more. That's why I think it's based on our knowledge. So the third one would be the frame attached to the Earth's center with orientation fixed relative to distant stars. Okay, so you should learn about the Foucault pendulum. You should know and look for it, search for it, know how it works and what does it actually prove. Okay, and why is this important over here? So this is an exercise for you to do. Let me put that in red. Learn about it. And the last one, so the fourth closest, which actually is the most useful for us. It's a frame attached to the Earth okay, and rotating with it at constant angular velocity. Angular velocity relative to frame in above, which means this one. Okay, so this is rotating with respect to this frame, and this frame is attached to the center of the earth. So you can get an idea. So most of the machines which you see around you are over here, okay, and the results are quite accurate if you work in this frame. So for all the engineering applications, we actually work in this one, in this frame, which we assume to be inertial frame. It's not exactly, but most of the machine works over here. Okay, so therefore whatever we understand as inertial frame, this is the one which is attached to the earth, okay, on the surface of the earth clearly, and it is rotating with a constant speed with respect to the center of it, because we just know for sure about the rotation of the earth and so on. We also know about the rotation of the center of the earth about the sun, okay, and perhaps the sun itself moves, okay, but we know little about the movement of the center of mass of the solar system as of now, and hence we assume that's the most closest to an inertial frame. And as our knowledge progresses, my guess is that there will be something which will be more closer than this, and hence this preference list will keep on coming down. However, even with that advancement, mechanics continues to remain useful, because this particular frame, it may be 4th, 5th, 6th, 10th, whatever we find later on, it has been shown to be reasonably work well, and the Euler's axioms have been valid. So for us, this will be the inertial frame always. Okay. So if you look at this equation 2.10, 2.11, in reality they are 6 scalar equations, okay, because there will be 3 directions of forces and 3 direction of moments, and so there will be 6 scalar equations, 3 over here and 3 over here and 3 over here. So let me now just put that note that the 6 scalar equations corresponding to equation 2.10 and 2.11 when applied to the whole system are not sufficient for determining motion of a general system which is deformable. And hence possesses an infinite number of degree of freedom. So the 6 scalar equations corresponding to these equations when applied to the whole system are not sufficient for determining the motion of a general system which is deformable, okay, meaning it's not rigid and hence possesses an infinite number of degree of freedom. Okay, so the number of independent constants which are required to exactly determine the motion will be infinite for a deformable body. Okay, but the good part about this particular course is that we don't have to worry about deformable systems for now. Okay, what we have is rigids. Okay, and these 6 equations, but these are necessary and sufficient for a complete determination of the motion of a rigid body. Okay, why is it true? Because a rigid body has exactly 6 degrees of freedom. Okay, so there are 6 degrees of freedom to be found out, and then there are 6 scalar equations. So the problem is exactly answerable. Okay, now there will be many situations and problems in which you will be learning about you will be learning about the application of this Euler's axioms, and we have to still make sure that there are some other criteria which are met. Okay, so the application Euler's axioms requires that the system is well defined and its sketch is drawn in isolation from the surrounding. The second requirement is that the external forces and moments applied by the surroundings on system should be drawn on it. Okay, the sketch which you have drawn over here, then you have to draw the external forces and moments on that, so that you can apply the Euler's axiom. Okay, and such a diagram is actually called the free body diagram. You already know about it. We'll just call it FBD from now on. So you do not have to ever show the internal forces, okay? So the internal forces are never shown in these. Reason? They do not appear in the Euler's axioms. Okay. So if you want to write the equation of center of mass of any system, okay, you using this Euler axioms. So let's see how we can do that. So the equation of motion of the center of mass C of any system is obtained using Pi from 2.9 in 2.10. Okay, so you have to use the definition of momentum from over here, okay, from 2.9. You already have it in terms of the center of mass over here, and you have to put that in 2.10. okay, so what would that give us? It would give us, let's see, it would give us the force. So, and then we had to write the time derivative of the momentum, that will be equal to mvc in I dot, okay, or this is mac of I, okay, and this is equal to for the individual masses, again by the same definition which we have used before, in 2.9, that would be MIACI in the I frame is equal to this, okay. So this is 2.12. Now this vector equation can be written into scalar equations depending on which frame you are working. So no, sorry, in which Cartesian coordinate system you are working. So if you are in the Cartesian system, so fx would be equal to mxc dot, where xc is the x coordinate of the center of mass, fy is equal to myc double dot, and fz is equal to mzc double dot, okay. Fr, so this is the cylindrical coordinate. In this we write as mrc double dot minus rc phi dot c whole square. I will write actually this in red. The purpose would be so that you should exactly know how this is written, okay. So if you do not recall, you have to actually pause this video over here and then go back and check how we are writing this fr, sorry, how we are writing this fr as mrc double dot minus rc phi c dot whole square. F phi is equal to m 2r dot c phi dot c plus rc phi double dot c, and then fz is equal to m ZC double dot. Okay, and similarly the tangential normal and the binormal direction, when this is the path coordinate. Remember, we had three coordinate systems: the Cartesian, the cylindrical, and the path. So Cartesian one is easy, that's why I've written them in black, but this is something which you should go back and check. Okay, the simple reason is that the acceleration in the binormal direction is 0. Okay, so this is equation 213 actually, the whole of it. Okay, so rho c is, as you know, is the curvature of its path. Okay. Now, don't get me wrong, this 2.12 and 2.13 is valid for any system. Okay, is valid for a system which may be rigid body, deformable body, or a system of rigid bodies or system of deformable bodies, or a finite or infinitesimal part of a body. Okay, so it's all valid. Only thing is that you will not be able to get a complete idea about the motion of the material points of the body if it's not rigid. Okay, if it's deformable, then you will not be able to do that, but the equations 2.12 and 2.13 are still valid. Okay, and you will see that this equation 2.12 is the core of the second law of Newton. Okay, Newton's second law, this equation 212, that we'll see later when this when we actually discuss this. Okay, so equation 2.12, equation 2.12 is the real content of Newton's second law. Okay, you perhaps knew this anyways, but we are just stating it as if you are learning everything now. Okay, now if the force, or it's not the force actually, it's the external force acting on the system, because we have defined it like this, is equal to 0, then if the external force at any given time is equal to 0, then the force is equal to, you already have written this as AC of I. Okay, over here we have already written that in 2.12. Now this implies that the acceleration of the center of mass in the I frame will be equal to 0, since the mass cannot be 0. Okay, and the MIACI in the I frame is equal to 0 for all times. Okay, so if this quantity is equal to 0, this entire thing will also be equal to 0. That's what we are saying. Okay, now this implies, if the acceleration of the center of mass is equal to 0, that it means that the velocity of the center of mass in the I frame at time t is equal to velocity of C frame, C center of mass in the I frame at t equal to 0. Okay, and the same applies over here. Mi vci actually, velocity of the center of mass of the ith body or the ith part of the system at time t is equal to mi vci at 0. So this all is 2.14. Okay, and in words we say this: the center of mass C of any system, okay, not deformable or not rigid, any system moves with uniform velocity relative to frame I if the total external force on it is 0. Okay, and this is not true for other material points. So other material points what can happen to the body? Other material points will not show this in general. Okay, that's moving with a uniform velocity. So the body may split, it may deform or rotate. Anything can happen depending on the nature of the body. If it's deformable, if it's straight. So if it's a rigid body, something else can happen. Maybe it can rotate. If it's a deformed body, it can split or deform. Okay, so something else can happen. But this statement that the center of mass of C of any system moves with a uniform velocity relative to frame I if the total external force on it is 0, this is only valid for the center of mass. Okay, not for a general point. That's the important point you can take away from this. And this statement is actually, let me put it in words, that this is the precise content of let's say precise content of the Newton's first law. Okay, so this is the precise content of Newton's first law. Okay, this is the precise content. Okay, that the center of mass will not have any acceleration, and this also is something perhaps you knew in some other way, but it has come now from the primitives, defined entities, and the axioms. Okay, now in addition, if in addition to meaning if f is 0, okay, then f at a given time t is equal to 0, and then the momentum at the 0th time is also equal to 0, then equation 214, this is 214, implies that the velocity of C at time t is equal to 0 Ci Rc of t is equal to Rc of 0. Okay, since the velocity is 0, you can say that the position vector of the center of mass also is not changing with time, and the same can be applied over here, that the mi Rci of t is equal to summation of mi Rci of 0. Okay, so this means that the center of mass C of any system remains at rest relative to frame I. Okay, so the center of mass of any system remains at rest relative to frame I. Okay, the only catch is, though parts of the system may move. Okay, so this entire summation, okay, this remains the same, or this particular entire summation remains the same. The individual parts can still have a positive and negative value accordingly, so that the final summation of all of them is actually equal to 0. So that's the meaning of that, though parts of the system may move. Okay. Now, one of the other things is that if for some reason, say you have f at t is equal to what, fx I hat plus fy j hat plus fz k hat. Okay, if say this particular thing is equal to 0, okay, then this implies then this 2.15 and 2.14, this will be valid only along the x direction or the I direction. Similarly, if this is equal to 0, then this 2.14 and 2.15 will be valid along only this particular direction. Okay, so these statements will not in general be valid. It will be only valid if the particular component is equal to 0. If all of them are 0, then clearly this is there. Okay, so for example, if this is not 0 entirely, okay, but is 0 only in the x direction, but in other direction is not, then you have to rephrase this entire problem, these entire equations in one particular direction. Same can happen with ER and E5 directions also. Okay, so there is nothing specific to mention about that. So the last sort of comment which must be made over here is that the kinematic variables A C of I and V of PA of I in Euler's axioms have the same value in all inertial frames. in uniform translation. With respect to one another. This implies that the forces F is dependent on the position, the velocity, and the time appearing in these axioms must be of the form F of R2 minus R1, R2 dot minus R1 dot, and T. So all forces depend on relative motion of relative positions and or velocities of interacting bodies. Okay, so you must try to answer this question, that why is it that if you have uniform translating inertial frames in uniform translation with respect to one another, that the variables ACI and VPAI will be having the same value. One hint which I should give you right now is that you can refer to the translating frame T. Okay, we had this discussion about the translating frame T, and perhaps from there you can try to pick it up. Okay, so please do this and convince yourself and move ahead only once you are clear on this. So this is not happening because you are being told to do this. We are following a very logical step of making claims like this. Okay, so please do it, and then you can move ahead. Now if we want to use the Euler's axioms which we have just discussed, one of the key parts which we haven't yet discussed is about our ability to calculate the external forces and the external moments. Okay, so we need to compute F and MO. Okay, so before that, let's just define something as a force system. This is a term which we will be using to refer to a load system consisting of forces and moments. Okay, even though this name only has force in the force system, but it means consisting all the forces and moments. Okay, now two force systems are said to be equivalent if they have the same total force F and the same total moment MA about one point Okay, so this is how we have defined the equivalent force systems. And the other option is that rather than writing all the forces and moments, we can have a resultant of it. So we can simplify a force system. So a simpler force system equivalent to a given force system is called its resultant. Okay, so if you have lots of forces and moments acting and we somehow are able to replace them by say a single force and a single moment, that would be called a resultant force system. Okay, so the following will hold for a equivalent force system. Okay, or rather I should say all of them. Okay, all of the following should hold. So if you have a force system and you want to find an equivalent force system, simpler or non-simpler, that's a different issue. Okay, this must definitely hold. So the first thing is that the equivalent force systems have total moment mb about any point b. So there is a way to prove this. So if you have a force system, let's call it Fs. Okay, so force system I'll call Fs from now on. Fs has n discrete forces with ith force Fi acting at point I and m couples with moments Cj. Now at this time, if you do not recall what the couple was, please go back and check. Okay, so where J will be equal to 1 to M. Okay, let's think of this like over here. Sorry, yes, let's just say that this is the body and this is the point B. Let's say this is the couple with a moment C1. This is the point 1 which has this has a point 1 which has a force F1. Then you have a point 2 for example which has a force F2. Okay, and then this can have a couple C2. Similarly the point N will have a force Fn. Okay, and say the point I over here, say the point I over here has a force Fi, and then this is a point B. This is the vector from B to I, and this is another point A. Okay, so a force system has n discrete forces, so F1, F2, F3, F4, Fn, okay, acting at point I, okay. So F1 acts at point 1, F2 acts at point 2, and 3.2, and Fn acts at point n. And M couples, so C1 acts at point 1, C2 acts at point 2, and say if this is point M, okay, so Cm acts at point M. So this is a couple with the moment C1, C2 to Cm, okay. And in general, say this is the jth point, okay, so this would have a couple Cj, couple with the moment Cj, okay. So that's the description of the force system over here. Now we want to write MB, okay. So this is the moment about point B. So this would be equal to any general moment due to a force would be written by the vector about the point B will be written by this vector, say Bi cross Fi. So this has to be summed over all the i's, and then there are already moments existing in the system, which is Cj, okay. Now this vector Bi, okay, so do remember, I mean, this is a moment due to a couple, this is the moment due to a force, okay. About the point B you write it like this, and this is anyways what is given, okay. Okay, now the vector Bi can be written as Ba plus Ai cross Fi. So this is a vector, okay, and the Cj remains as it is. So Ba cross Fi summation over I plus Ai cross Fi summation over I plus Cj, okay. Now this Ba cross summation can be taken inside. The reason is the vector Ba is independent of I, okay. So for any given I, vector Ba remains the same, so it can be, the sigma sign can be taken inside over here, and this particular quantity is actually just like you have defined MB as equal to this, okay, this particular thing in the square bracket can be written as MA, the moment about point A, okay. Now the last part is that Ba remains as it is, and the summation of all the external forces discretely is actually equal to F, sorry. Now you should recall where we had said that sigma fi will be equal to f. Okay, f is the summation of all the external forces. Now just about this, this implies that the moment mb for equivalent force systems is the same since f and ma for them are equal. Okay, so this is the given force system. Now if I draw an equivalent force system, I can have any combinations of fi's and cj's, okay, and they will be considered an equivalent force system if the total force is same, okay, and this ma is the same. Okay, so f and ma for them are equal. Okay. The reason for that is the vector BA, for example, will still remain at the same place, right? The vector BA will remain over here, and MA is anyways the point A. So that's why the moment MB for equivalent force systems is the same, since F and MA for them are equal. Okay. So this is a proof which had these discrete forces and moments due to couple. The same can be extended if you have a continuous distribution, okay, of forces and moments. So for finding the moment, moment sum and force sum a given force system can be replaced by its resultant. So we will see the example of it more. Okay. Eventually, this moment sum and force sum is required in the use of Euler's axioms. So that's where you replace a given force system by its resultant force system. Okay. Now, the second point is two equivalent force systems impart the same motion to a single rigid body. Okay, the reason for this is that since the external forces and moments are the same, so the motion of this rigid body will be the same. Okay, however, internal forces which are there, so the Euler's axiom only concerns itself with the external forces and it predicts the motion of a rigid body, but internal forces can be different for the same motion of this rigid body. So let's consider a case over here that you have this rigid bars. Okay, I am mentioning the word rigid so that you don't take it as elastic. So you have one situation in which there is, sorry, P1 and P2. Okay, so this is obviously in tension, and the same rigid bar, if it has P1 and P2 like this is a compression. Okay, so the external forces, the resultant external force acting on this are same. Okay, that's P1 minus P2, and hence according to the Euler's axioms, the motion of this rigid body should be the same in both the cases. Okay, but if you cut a cross section, say somewhere over here, okay, and then you cut the same, hypothetically cut this cross section over here, the internal forces at these points will be different. Okay, so clearly over here there will be a feeling of tension. Okay, the motion of the force will try to pull it, and in this case the force will try to push it. So that is the meaning of that, the internal forces induced are different, though the overall motion of this rigid body will be the same. Okay. Now the third point, so if you have two equivalent force systems, in general impart different motion to a deformable system. And to a system of rigid bodies. So if you have a deformable system, okay, so say if this bar over here was elastic, okay, then each material point of it would be having a different motion, okay, compared to a rigid one, in which case it would be the same over there. But this is also true of having different motions even for a system of rigid bodies. So if you have, say, a rigid body like this and it is connected over this joint like this with another rigid body, and then you have the same situation over here and you have the same situation over here. So these two bodies are rigid, but they are connected by this joint over here, which will allow basically a rotation of these two. Okay, so this angle can keep on changing. Now if you apply the force F like this, and you apply the force F like this, okay, you will have a different motion. Okay, so for example, this particular point will be moving up, and somewhere over here this will also be moving up. The same point over here will be moving down. Okay, and hence even for a system of rigid bodies, the motion will be different, and that's the meaning of this word single rigid body over here in the point 2. Okay, they impart the same motion to a single rigid body, not to a system of rigid bodies. Okay, now another sort of derivative of this particular statement is that if the system of rigid bodies together form a rigid system. So if you have to understand this system of rigid bodies actually has a deformable system, okay, meaning the shape and the size of this will change as the force is applied, so it is deformable. But if you are able to create a system with a system of rigid bodies, you are able to create a system which overall is rigid, then the equivalent force system produces the same motion. So just to point out that these two are the equivalent force system, okay, they are equivalent force systems. And how do you know? You can check the moments and forces, so you will get the same answer about any point which you want. Now which point you should choose, you can think about it. Okay, I think this point looks nice enough, this point of the joint. Okay, so now we have to see about this rigid system of rigid bodies creating a rigid system. So let's have a link like this, let's have a link like this, and so joint 1, joint 2, joint 3, similarly joint 1, joint 2, joint 3. So if you have this force acting like this and another force acting on this, okay, now this separation between the two is D. Similarly, if you have this F acting like this, okay, F and F by 2 acting like this, and the distance between them is 2D. Okay, so these two, so first of all you should verify that these are equivalent force systems. Okay, you have to do that first, that they are actually equivalent force systems. I'm sorry, this is F by 2. Okay, do remember, when you try to calculate the moment, please choose the same point in this and this. You can't be choosing two different points. Okay, so you must be choosing the same point. Okay, sorry, this is okay. Now once this is done, you have to now confirm that they actually form a rigid system. A rigid system in the sense that the system as a whole will not be deforming. Okay, and that is quite obvious with the figure over here, because you can see how the forces are acting. So this system itself will not be deforming, unlike this particular case which is over here. Over here there will be a clear deformation. So this is a logged, somewhat of a logged system. Okay, there is no motion allowed, because I mean, if these rods which you have, if they were deformable, then there was clearly a possibility of something happening. But if all these three are rigid, the system as a whole is also rigid. It will not change like it does in this particular case, which is at the top of this. Okay. So in this case, the motion will be the same. So this system and this system will create the same motion of it. So as a whole, it can move anywhere it wants, but it will be the same motion, or it cannot move anywhere at all. Both of them are possible. In both cases, it will be the motion will be the same. Now for the purpose of equivalent force system, the force is a transmissible vector. Okay, so just assume that I have drawn the same body. Okay, it's hard to do that. So when I say for the purpose of equivalent of force system, the force is a transmissible vector. So if you have this at point P, you have this force F, then you can just assume that at Q you have this force F, as long as Q lies in the same line as that of P. So this is the meaning of a transmissible vector, but this is only for the purpose of equivalent forces, equivalent force system. Okay. The reason this is there, because I mean, whatever effect this creates on this rigid body will be exactly the same as that created by this on this rigid body. That's why we are saying that it is equivalent force system. Okay, because these are single bodies, single rigid bodies to be specific. Okay, and clearly the external forces and moments will not change whether you calculate them about point P or you calculate them about point Q. Okay, so and with this particular thing we have seen several times that it does not really matter as long as the line of action of the force is the same. Okay. This is only true for a rigid body. Okay, for a deformable body, let me write what is not of any meaning. The magnitude the line of action and sense of a force are significant for its effect on motion of a rigid body. And its point of application is immaterial. Application is immaterial, okay? So whether it acts at P or Q, it won't really matter for a rigid body. So this is clearly not true for a deformable body. So for example, if you take this sort of rubber, okay, and then if the force F is applying, say you keep on this this on a table, your rubber eraser with which you rub your pencil marks, okay, just call it an eraser, and if you just keep it on your table, it will have this force F acting that may be equal to the weight of this particular eraser, okay. But now if I remove this particular table from below it, okay, and say apply the same force over here, F, okay, this at this point, over earlier we were applying the force at this point, now we are applying at this point, okay. So clearly the motion of this will now be different. Now there is no table, okay, and even though it is on the same line as that of before, the motion of this will be different, okay. So the motion will be different in this case, deformable. What will happen is that this particular part will be pulled, okay, so this will be under a lot of tension, this part, and over here the same will not be true, hence this particular point the motion will be different as it was over here. Same will not happen in a rigid body, okay. So force is, I mean, I should write it in red. Force is not a transmissible vector for its effect on a deformable body. Okay. The same definitions, or I will write just say similar definitions hold true. Similar, same holds true for moment or couple of moments couple of moments. So this is a transmissible vector for a rigid body, but not so for a deformable body. So these these are all rigid cases. Okay, you apply f like this, you apply f like this, and this distance is d. Same case, you apply 2f at this end, and you apply 2f at this end, and this distance is d by 2. And the last, or I mean many possibilities, but three cases which we are seeing, this is 2f by 3, this is 2f by 3. Okay, you should be able to find what angles they are. Okay, if it has to be equivalent to this one. So these are all equivalent moments. Okay, and they will have the same effect on this, and because they were transmissible, so you could have had any change and it would produce the same effect. Now if you again consider a deformable body, sorry, let me do that over here. Okay, so say this is the eraser. Now if you apply a couple over here, or in the other case you apply the couple over here, okay, you yourself know that over here the twisting will happen somewhere at the top, over here the twisting will happen somewhere at the bottom, so they cannot be equivalent, they cannot be the same motions. Okay, so moment is not transmittable. Okay, or a couple of moments is not transmittable in a deformable body. The same for that of the same as that for the force. Okay, let's take up the fourth point. So the resultant, which is actually the equivalent. So we call a resultant as equivalent when it is simpler than what is given. Okay, so the resultant equivalent of a given force system at a given point A consists of a force Fr, okay, and an associated couple with moment CRA. And how would you find them? Well, the resultant force is Fi, okay, summation, and CRA, the resultant couple, okay, is equal to MA is AI cross Fi plus Cj. Okay, so this we have already seen. before. So this is equation 2.16. I mean, how do we find this? We have already seen. We had done it for MB. The same definition holds for MA, any other point. Now you will notice that even though the resultant equivalent of a given force system at a given point A, okay, consists of a force Fr, you see this given point A does not actually appear in Fr. Okay, so the reason is that this is independent of A. It's only the moment when you calculate these moments you require this point A, so it will depend on A, and you can see that it clearly depends on this vector AI. Okay, any discrete point. Of course, these summations can be replaced by integrals where you have a continuous distribution of forces and couples, so you should be able to do that yourself. So let me put that in writing. How would we write 2.16 for continuous distributions? Okay, not discrete ones like over here. You should try to think about it and perhaps come up with an answer. So you can pause it for now and see if you can try to answer. Line distribution, area distribution, volume distribution, all of them you should be able to write. Okay, now in the first one, I mean, let me write that in blue, green. So this will become FL ds, it's the path coordinate. This would be Fs dA, this is the area coordinate, and this is FV dV volume. Okay, similarly, I mean, this will be the resultant force, and similarly on this side one will have, say, for the linear distribution or the line distribution, one may have this cross FL plus ML, okay, over this path, small uh, distance ds along the trajectory. This would be RQA cross FS plus MS. So these are the surface moments MS, and over the volume, so we are taking these separate points. Okay, S is the position of a point on the trajectory, Q is the center of a small area ds, okay, dA, sorry, okay, and similarly P is the center of a small volume dV. So you should be able to draw a figure which shows all of it. Okay, so please draw a figure for each at this stage. Showing this. So you will require 3 separate figures. One for line, one for area, the other for volume. And the units you already know for ml, ms and mb. It will just keep on changing because you add one more dimension of length each time. Okay. So this statement which we have just made, let's summarize that in using a figure. Of course, let's try to write with a black ink for the discrete part. So say you had point 1, F1, so you have point I, Fi, and you have say point N as Fn, you have point J as a Now this is a force system. The equivalent of it about the point A would just have this Fr, and it would just have CRA. Okay, so CRA actually has all the moments of the couple, and it also has the moment due to the forces FIs. So both of them are there in this CRA, which is in this equation 2.16. One can do a similar diagram for continuous distributions. Okay, this was for a discrete one. Now for a continuous distribution, say you have this line S, and then this region is ds, and this has a MLds as its moment, and it has a FLds as its force. Similarly, say you have this small region over here, that region is small area dA, this point inside this is Q, okay, point over here is S, and at this Q you have this MS dA, FS dA, okay, and similarly one can have a volume. So this point is, this is small volume dV, this point is P, this point over here is P, and FB dV is force, MB dV is the moment, okay, and say you have this point, all this is being done about this point A. So the vector RSA would be this vector AS, vector RQA would be going from here to here, and RPA would be the vector AP. Okay, so obviously the total volume is V, the total surface area maybe S, okay, or A actually. Oh, I should not use A because I have done, and you already used a point A, but total volume area is also known, okay. So that's where you can draw this using a picture, the ones in green. So clearly this FR which you see over here, let me draw a better one. Fr will have some angle. So Fr is a vector, so it has its component Frx, Fry and Frz. So you must be aware at this stage what is the direction cosine of Fr. Okay, so we used it using L, M and N. So L is cos alpha and this is Frx by Fr. Okay, so this is essentially the orientation of Fr with respect Frx with respect to Fr, and similarly you would have M is equal to cos beta is equal to Fry by Fr, and N will be equal to cos gamma is equal to Frz by Fr. So in three-dimensional space, we do it something like this. For a two-dimension case, you already know that, say, if you have this as your Fr, okay, and this is Frx, this is Fry, okay, and this is angle theta. So you say that Frx is equal to Fr cos theta, okay. So cos theta will be equal to Frx by Fr. Now the same can be done, say, in the y direction. So Fry is equal to Fr sine theta, or you can write it in terms of cos of theta, okay, or let me just call it cos of 90 minus theta, okay, this particular angle. And similarly one can do it about the z-axis. So this is what a direction cosine is, if this is the first time you are learning about this. Okay, in a three-dimension case it makes much more sense. So the idea is that if you know the direction cosine of Fr, you know all the components. Okay, so Fr is a vector which will be Frx I hat plus Fry j hat plus Frz k hat. Okay, now Frx, you can, if L is known or cos alpha is known, this will just be Fr into cos alpha, this will just be Fr into cos beta, and this will be just Fr into cos gamma. So the direction cosines actually give you the individual components of this vector, okay, Fr, the resultant force. So in a similar way you will have the direction cosines of CRA, okay, for CRA. So please note that you should not use the same symbol L, M, N or alpha, beta, gamma when you calculate amount for CRA. Okay, that's a separate vector in itself. So it should have its own symbols of L, M, N or alpha, beta, gamma, whatever angles you take. Don't take it, I mean, call it alpha dash, gamma dash, beta dash, or L dash, M dash, and N dash. But it has to be a different symbol because you are referring to a completely different vector. Okay. Let's now come to the fifth postulate. I hope you take a pause somewhere and you are actually revising the postulates which we have just discussed. Okay. Sometimes it may be overwhelming if we just keep on going line by line, but you should pause and just revise back from the texts. Okay. The simplest resultant or simplest equivalent of a given force system is a wrench. Okay. If you do not know what a wrench is, now is a good time to Google to do a search of this word called spanner. Okay, and just look at the images which come up on your internet, and this should tell you what a wrench is. Okay, so this is the simplest resultant of a given force system. It cannot get any simpler than this. Okay, so please look up what this is, a spanner, over the internet. Just look for the image of a spanner and you will understand what it is if you have never used it. Let's prove that it is actually the simplest resultant. So let the resultant at point A be FR and CRA, and let the resultant at point B be FR CRB. Okay, remember the A or B will not come in the equivalent or the resultant force. That can be written, say, over here, where this is FR, this is point A, okay, and CRA. B is FR this would be CRB. Okay, now you can obviously write CRB in terms of CRA. That would be CRA plus the contribution of the forces, which is the vector BA cross FR. When we say FR, we refer to this particular resultant force. Okay, so BA is over here cross FR. Okay, so let's write MB is equal to CRB. This is equal to CRA plus PA cross FR. Okay, now I want to break up CRA into a parallel and perpendicular component. So this is parallel plus CRA perpendicular plus BA cross FR. Okay, let's call this as equation A. And when I said parallel and perpendicular, or parallel and normal are with respect to FR. Okay, so CRA parallel will be parallel to FR. CRA perpendicular will be normal or perpendicular to FR. So this is with respect to FR. Okay. Now if you look at this particular equation A over here, okay, you can try to cancel these terms, okay, by choosing appropriate B. So by choosing an appropriate P the last two terms on the RHS of equation A can cancel. Do recall that PA cross FR will be actually perpendicular to FR, which means the same direction as CRA perpendicular. So they are the same directions. So the direction is exactly the same for BA cross FR. Therefore, it should be easy to find an appropriate B so that the numbers or the magnitudes get cancelled. Okay. Let's see that now on a diagram again. So you have A, CRA, this is CRA normal, this is sorry, draw a thinner one. This is CRA parallel. Okay, and this is CRA parallel, so it is automatically in the same direction as FR. Okay, now if the point B, which we have just discussed over here, is actually a point D, point D is such that this blue term, this thing gets cancelled. Okay, let's call that point D, and in this case we will only be having FR, which will be equal to CRA parallel. Okay, only this particular term will be remaining. And let's call this distance as D. Okay, this angle is perpendicular. The plane in which all this is happening is the plane pi. Plane is perpendicular to CRA. Okay, so CRA is so because this is all referring to a three-dimensional situation, and you can imagine that this plane is actually the plane of your screen, and CRA is CRA perpendicular is something which is coming out of this screen. Okay, that's one way to visualize this. The vector, sorry, the length D is equal to AD is equal to CRA perpendicular by FR. Okay, so CRA perpendicular will be FR into D. Okay, so For this one, by choosing an appropriate B, the last two terms on the RHS of equation A can cancel. Okay. For such a point, say D, okay, we have already shown D, the resultant is a wrench. So what does a wrench consist of? It consists of an FR and a CRA parallel to this. So point D. This is the simplest situation that you can get rid of the perpendicular, get rid of basically these two terms. Okay. So at D you have the wrench. And how, if you look at the figure of what a wrench or a spanner is, you will exactly understand why FR and CRA parallel are the forces which act during the action of a wrench. Okay. There is a resultant force, and in the same direction you have a resultant moment. So it is normally used for tightening or loosening of bolts. Okay. So this follows that if CRA is parallel to 0, is equal to 0, that is if CRA dot FR is equal to 0. So CRA parallel is basically the projection of CRA along FR. Okay. Then I think the whole logic behind putting this vector sign over 0 is that if the left hand side is a vector, the right hand side should also be a vector. Similarly, if the left hand side is a scalar, the right hand side should also be a scalar. So I think it's a good practice if you do it like this. I'll also keep this in mind. Okay. It follows that if CRA parallel is equal to 0 vector, and that is if CRA dot FR is equal to 0, then the simplest resultant is a single force FR if FR is not equal to 0. Or a single couple CRA if FR is equal to 0, or a null system. If FR is equal to 0, CRA is equal to 0. Okay. So rather than having FR or CRA parallel, you can just have one of them as well. Okay. Or you can have none of them, which is both FR and CRA would be equal to 0. So a single couple can also exist as CRA. Okay. Now if you have say a system like this, in which at one point, say O, you have F1, you have F2, you have Fi, okay, and then you have this resultant Fr, and the last one, say maybe Fn. The simplest resultant of a concurrent force system is a single force. So these are all derivatives of what we have just done, okay? Derivatives of saying that the simplest force configuration is that of a wrench, okay? So this is just more simplified than that, as the simplest resultant of a concurrent force system is a single force, okay? Obviously it has to be through the point of concurrence, which is A in this case, okay? Let's take up say you have the X and Y. Point 1 you have F1, point 2 you have F2, okay? So these are basically coplanar forces. You can see that this is Ri, okay, and says you have this n point, so Fn is acting. This is the xy plane, this is point O, this is Z, okay. A coplanar force system consists of forces in one plane say xy plane and couples with moments along the normal to this plane that is parallel to Z. So a coplanar force system consists of forces in one plane, say xy plane, and couples with moment along the normal to this plane. So let me show the couples over here. They are C2 k hat, and in general we can write a Cj k hat. Okay, not showing the vector sign because k hat itself is a vector. Okay, so these are this is a coplanar force system. Now in this system, CRO dot So sorry, the resultant moment about O dot fr is equal to MOZ, sorry, MOZ by K dot, what is fr? It would be fx I hat plus fy j hat. This would be equal to 0. Okay, so because k dot I and k dot j will both be equal to 0, and this value CRO is calculated again by taking the summation of CJs and the summations of Fi cross, sorry, Ri cross F. Okay, so this condition gives CRO dot Fr is equal to 0. Now you have to look over here that this, it follows that if CRA parallel is equal to 0, so if CRA dot FR is equal to 0, so you can see that CRA or O in this case dot FR is equal to 0. So this condition also holds that the simplest force system will be this. When CRO dot FR is equal to 0, sorry, 0. Okay, this is coplanar force system. So I hope these green parts are clear to you. Okay, so this we have shown that this result, that the simplest resultant is a single force if Fr is not equal to 0, or a single couple if Fr is equal to 0. Okay, so you can either have the single force or the single couple. So if you want to draw the resultant of this, you must now say come up. So let me draw it over here. This is Z. So this is Z, yes, and this can be O. This is the arrow CRO. So this is a resultant at O. Okay, which is essentially the resultant force and the moment. Okay, and point A over here is FR this is B, so this is about point B. Okay, that would be 0 comma minus B comma 0, and say this distance is D. So we have already done this exercise several times. Okay, Over here I can do the same. So this is just a coplanar system. Okay, what I'm drawing over here, let me draw that in blue. This is a coplanar, sorry, parallel forces. So F and F separated by a distance h. So C1 is equal to minus FH. Okay. So in this particular case, also you will have this CRO dot FR will be equal to 0. So this will also be true, this statement which we have just written, also for parallel force system. Parallel force system. So please verify this, okay, that this is actually true. It's much easier thing to do compared to what all we have done. Okay. Now let's see for if Fr is not equal to 0, then clearly the line of action of the simplest resultant Fr is equal to Fx I hat plus Fy j hat is at distance t from O. This is the distance t from O. Okay. So if Fr is not equal to 0, the line of action of the simplest resultant source Fr is equal to Fx plus Fy is at a distance d from O, and some relationships exist between these A, B, C, D. So for example, just look at AFY is equal to PFX is equal to DFR, okay, equal to MOZ equal to obviously CRO dot K hat. Okay. Now say you can find anything like this. You can use for example, something like this. You can use suitable triangles. Use suitable triangles. So this is some part of geometry which you have learnt in your school, okay, to derive all these things. At least these things. Essentially the angles are what you have to think of, okay. So this is Fy, this is Fx, okay, and then you can choose any angle over here, and then first choose something like this, and then this entire triangle. So whichever way you do, you should be able to do this, okay. This should imply that D is equal to MOZ by FR, A is equal to MOZ by Fy, and B is equal to MOZ by Fx. tan alpha is equal to Fy by Fx. I'm sorry, what I had described over here in blue was not actually for a parallel force system. I should make that correction over here. This one is just a definition of what a couple is, okay? Parallel force system is done in much greater detail. So, okay. So this is C1 is equal to minus FH. So this is just the definition of what C1 is. Okay. So for dealing with a parallel force system, we have to separately deal with this. So let's have a parallel force system. So this consists of forces parallel to a line. Say, what is the line? Is the z-axis, and couples with moments normal to this line. Okay, so if it's normal to this particular line, then it will have components along the I and j or x or y direction. So CRO dot FR is equal to MOX I hat plus MOY j hat dot FR k hat. This will be equal to 0. Okay. Now for FR not equal to the 0 vector, the simplest resultant k hat intersects xy plane at a comma b comma 0. Okay, so ai hat plus bj hat cross fr k hat is equal to CRO is equal to MOX I hat plus MOY j hat. So let me draw this, okay, so that it becomes slightly clear. Let me have the XY axis first. X is over here, okay. So the forces are parallel to the z-axis. So this is the z-axis. Say F1 is over here, Fi is over here, okay, and similarly Fn is over here. Okay, so the forces are parallel to the line which is where the z axis and couples with moments normal to this line. Okay, so the couples will have components in the I and j. So let's say this is the Ci. Okay, okay. Now CRO dot couples with moments normal to this line that is having components along. So this is okay. So Ci is the couple. You can have C1, C2, C3. I mean, it won't really change anything. Okay. Z axis. Okay. So if you can have, for example, I mean Ci, it can C2 can, for example, also be something like this. Okay. This is like still perpendicular to the Z axis. Okay. So that is also a possibility of a parallel force. Now CRO dot FR will be equal to MOXI hat plus MOYJ hat dot FR K hat. That quantity would be equal to 0 because of the dot products. And then this simplest resultant, let me draw that over here, should be Y, X, Z is always FR and CRO. Okay, I can draw this CRO on this XY plane because I know that it will only lie on the XY plane. Okay. Okay, yes, the equivalent CRO, and similarly this is because of this. Okay, so if you want to find FR, okay, you have A, you have B, you have this point A which is A comma B comma C. Okay, and B would be equal to MOX by FR. So okay, so this is simpler to write. To see this, you can just see about this how the dot products and the cosines play a role. Dot product essentially gives you a cosine, and that's where the direction cosines come up. Now, despite the fact that the simplest resultant is actually a wrench, which is FR and CR parallel, okay, but it's not necessary that we use it all the time, because many times it will be convenient to choose it, find the equivalent about some other point which may not actually be a wrench. Okay, so remember, for a wrench you had to make this term as 0, okay, hence you chose your point B as D such that this gets cancelled. Though it is mathematically looking very nice, but physically many of the situations may not require us to go to this, and we may choose another point which may not be a wrench, but still it will be convenient over there. Okay. Okay, now we must also be learning about the internal force resultants. Since we have learned about external force resultant, we must also do this uh, just for the sake of our knowledge and better understanding. Though, as you know, for Euler's axioms we only require the external forces or external force resultants. But we want to also know about the internal forces briefly, okay, just so that we have an improved understanding of what is going inside our concerned solid. So if you have, say, this body 1, let me put this, let me choose a nice shape because I have to draw it again, okay, and then this has a couple moment C, force P. This dotted line actually shows this the dotted line actually shows this hypothetical cut. Okay, so every time you want to calculate an internal force, you must make this hypothetical cut into two parts. So you have forces PQR acting on this body, couple is moment is C, okay, the direction is shown, and now you want to find, say, what is internally happening over here in this point. So for that we take up this point as C star, which is the centroid of this area, okay, take up C star, okay, minus CR FR, and this is point 2, so body 2, part of the same body, okay. Again, I must emphasize that we have not actually cut it into two halves. We have hypothetically cut it because we were interested in finding the internal force resultants. Okay. So the internal point is shown on this plane. So for an internal section of a body, the distributed force across the section can be replaced by its resultant at centroid C star of the cross section. So at C star you can have a FR and minus FR shown. So FR, okay, and you can have a say minus CR, sorry, plus CR, okay, so that on the other side you have a minus FR and minus CR. So this is how you can have an internal force resultant, okay, force resultant at an internal point. So if you take up a thin bar, let's see how we can so this is say the thin bar, okay, so this is a C star, okay, that's one problem with this. Okay, so this is the area, this is the centroid C star, okay, so this is now first, this is the second, because the hypothetical cut, so I should have drawn this by a dotted line, but I am drawing it by the solid line. It's still a hypothetical cut. Centroidal axis. Okay. Now let's see them separately. So clearly this is P, this is Q. Okay. Over here we must have at the centroid CR, we must have a FR. Similarly on this side, this is already a C, this is the second part, this is the first part, okay, this is a R, and over here we have this minus of CR and then F minus of FR. Okay. Now just to have a coordinate system in terms of which we can write this FR and CR, let's choose one along the tangent, so tangent of this axis, okay, that as ET. Obviously the one normal to this would be EN, and then you have the binormal, which is EB. You clearly know that EB will be perpendicular to ET and EN, okay. So you want to resolve your Fr as equal to Ft Et plus Fn En plus Fb Eb. Okay. So this Fr can be resolved. Similarly, this equivalent Cr can be resolved as Ct Et hat plus Cn En hat plus Cb Eb hat. Okay. This is equation 217. Only thing is, you must know that they all pass through the centroid. Okay, the fixed this coordinate system is attached to the centroid of this. Okay, so that you can resolve these forces. So in general, we say that the centroid, okay, is chosen as the base point for the internal force resultants. Okay. So if you have, say, a situation like this, R, this point is A, this force is P. Okay, let me draw the centroidal axis also. Let's make this hypothetical cut at B. You have force Q, you have this C, and you have D. So this point B, and then you have the point A, and you have R, you have B. Okay. Similarly, let's draw the other half of it. This is D, this was C, it was Q over here, and this is again B. So I am drawing some things which I will define right now. I'll draw this N, I'll draw a S at B, and I'll draw a M. I'll draw again a N, I'll draw a S, and I'll again draw a M. So the axis and the transverse components of FR are called the axis or the axial. I think that's the more correct one. Component of FR, okay, FR would be the resultant force at B, okay. So we have resolved them into two parts, one is axial, one is transverse. It is called the axial or the normal force N, and shear, since this is the first time, let's use shear force S, okay. Now N, what does it intend to do? It tries to pull apart, pull or push the rod. So this is a rod, okay. And what does S do? Tries to tear apart the rod transversely. Okay, so example is cutting a paper using scissors. That's an example of the shear force. Okay. Similarly, the axial and the transverse components of CR, okay, the equivalent moment is called the MT, which is twisting moment. This is axial, okay, and MB, it is the transverse. This is transverse. Sorry, this is a bending moment, I'm sorry. Bending, and this is transverse. Needless to say, MT is the one which tries to twist, okay, and MB is the one which tries to bend. And the names are already clear about it. So we can resolve them. So for example, N will be, so if you have seen the coordinate system, to find N, I must resolve FR along ET, okay. Similarly, to find MT, the twisting moment along the along the axis, essentially, will be resolving CR along T. So please don't get confused by this normal axis and the normal forces. The normal forces are actually, so they are acting, N is acting along this axis, which is the centroidal axis, okay. So please see that, don't get confused with this En as the normal direction, that's not, okay. So N would be equal to, no, it's this space over here, perhaps I should do that. Let me do this over here, okay. Let me do that with green. This is 217 anyways. So N would be equal to FR dot ET, okay, and this would be equal to FT. Similarly similarly S would be equal to FR, okay, minus FT ET, okay. So you can write FR as this and just find the value of S over here. So that's there, and similarly you can have, so the magnitude of the shear force would be Fn square plus Fb square 1 by 2. So this would come in if you just substitute this Fr from over here. This is something which will come out. Similarly, Mt will be equal to Cr dot Et equal to Ct. Mb is equal to Cr minus Mt Et hat. Okay, so this is equation is called 2.18, and Mb is equal to Cn square plus Cb square. Again you have to put Cr of here, from here to over here, and then you will get this magnitude of Mb like this. So if you have a bar which is say you have a bar with a plane centroidal axis, say in xy plane, and you have a coplanar system, coplanar force system in the plane of centroidal axis. The components of FRZ, CRX, CRY of FR and CR are 0. Okay, so let's see how that can be shown in a diagram. So if you have, say, okay, you have a uniform loading like this, F, and along the axis this point T, and you have this load C. Over here you have the force P. Okay, and say you are trying to study the internal forces at B, so you would take up again over here, and then you would write this as okay, B N M, and the shear force would be shown. Clearly F is given over here, and then A is this point. Over here you have A, and the other part of it can be drawn. So this is a centroidal axis. Okay, and that would be C, this is D, this is again S, N, and M. Okay, so B, and then you have this point P. So this is the Q is the force distribution density, okay, force per unit length. So this is what we mean. If you have a coplanar force system in the plane of the centroidal axis, the components of FRZ, CRX and CRY will also not appear. Okay, so this will just not appear because there is no component of F in the Z direction. Okay.